The National Electrical Code, or NEC, sets forth regulations regarding raceways for communications circuits, aligning them with the general requirements for electrical raceways outlined in Article 300. This encompasses rules pertaining to bending, detailing specific criteria for how conduits must be manipulated to maintain electrical safety and system integrity. Section 300.34 addresses bends and elbows, prescribing methods and limitations. Subsection A, titled Bends, mandates that rigid metal conduit, electrical metallic tubing, or intermediate metal conduit must be bent using a bender designed specifically for that purpose. This stipulation ensures that the bending process does not compromise the structural integrity of the conduit. The code explicitly states that conduit shall not be bent in a manner that will cause damage, preventing deformations or weaknesses that could affect its performance. Subsection B, titled Elbows, addresses bends of less than 360 degrees. It states that these bends must be made with approved elbows or listed conduit bodies. The use of approved elbows or listed conduit bodies ensures that the bends meet safety standards and maintain the integrity of the raceway system. Section 300.37 focuses on the number of bends allowed in a raceway. It sets a limit on the cumulative bend angle within a run of conduit to prevent excessive pulling tension on conductors, which can lead to insulation damage and potential electrical hazards. For conduits of trade size 1/2 inch through 1 inch, the code permits a maximum of 4/4 bends, equivalent to 360 degrees. This means that the total angle change along the conduit run cannot exceed a full circle. For conduits larger than 1 inch, the allowed number of bends is reduced to 3/4 bends, which equals 270 degrees. This reduction accounts for the increased stiffness of larger conduits and the potential for greater pulling tension on conductors. An exception exists where a single run of conduit is installed to connect a raceway containing more than 12 individual conductors to a panel board or other enclosure. In this specific scenario, the number of quarter bends can be increased to 8, totaling 720 degrees. This exception acknowledges the complexity of connecting large conductor bundles and provides flexibility while maintaining safety. These requirements apply equally to communications conduits as they do to electrical conduits. The NEC does not offer an exception that would permit a communications conduit to exceed a total bend angle of 360 degrees without the inclusion of a junction box or conduit body. The reason for these limitations is to ensure the proper installation and operation of electrical and communication systems, maintaining safety and reliability. Excessive bends increase the difficulty of pulling conductors through the conduit, potentially damaging the insulation. Damaged insulation can lead to short circuits, ground faults, and other electrical hazards. Moreover, exceeding the allowable bend limits can compromise the structural integrity of the conduit itself, reducing its ability to protect the conductors from physical damage and environmental factors. The use of approved elbows and listed conduit bodies ensures that bends are made in a controlled and safe manner, maintaining the raceway's integrity. These components are designed to provide smooth, gradual bends that minimize stress on the conduit and conductors. In summary, the NEC mandates that communications conduits, like electrical conduits, adhere to strict bending limitations. The total bend angle within a conduit run must not exceed 360 degrees unless a junction box or conduit body is used to break up the run. This regulation is in place to prevent damage to conductors, maintain the integrity of the raceway system, and ensure electrical safety. To comply with the NEC requirements, install communications conduits with bend radii that do not exceed 360 degrees or incorporate a junction box. This approach ensures that the installation meets code standards, prevents potential electrical hazards, and promotes the long-term reliability of the communications system. Now let us delve further into the specific sections of the NEC to clarify and expand upon the requirements for conduit bends, particularly as they relate to communications systems. Section 300.14 Length of free conductors at outlets, junctions, and switch points requires that a sufficient length of free conductor be left at each outlet, junction, or switch point for making connections or splices. While this section does not directly address the number of bends, it emphasizes the need for accessibility and workability of conductors, which can be affected by excessive bends in a conduit run. A large number of bends can make it difficult to pull conductors, leaving insufficient free length for terminations, thus violating 300.14. Section 314 Outlet, device, pull and junction boxes, conduit bodies, fittings, and manholes provides detailed requirements for the installation and use of boxes and conduit bodies. These components play a crucial role in managing conduit bends and providing access to conductors. Section 314.16 Number of conductors in outlet, device, and junction boxes specifies the maximum number of conductors permitted in a box, which is determined by the box size and the conductor size. This section is important when planning conduit runs with multiple bends, as each bend increases the pulling tension on conductors, potentially requiring larger boxes to accommodate the increased conductor fill. Section 314.22 Conductors entering boxes, conduit bodies, or fittings outlines the requirements for how conductors must enter boxes, conduit bodies, or fittings to protect them from abrasion and damage. This section emphasizes the use of bushings, lock nuts, and other fittings to ensure a smooth transition for conductors entering and exiting the conduit system. Excessive bends can exacerbate the risk of conductor damage at these entry points, necessitating careful attention to detail. Section 314.28 Pull and junction boxes and conduit bodies provides specific requirements for pull boxes, junction boxes, and conduit bodies used in conduit runs. These components are essential for breaking up long runs of conduit with multiple bends, making it easier to pull conductors and maintain code compliance. 314.28 It provides minimum size for straight pulls. In straight pulls, the length of the box or conduit body shall not be less than 8 times the trade diameter of the largest raceway. This requirement ensures adequate space for pulling conductors straight through the box without excessive bending or stress. Section 314.28b provides minimum size for angle or U-pulls. Where angle or U-pulls are made, the distance from the raceway entry point to the opposite wall of the box shall not be less than 6 times the trade diameter of the largest raceway, plus the sum of the diameters of all other raceways entering on the same wall. This requirement provides sufficient space for making angled pulls without damaging the conductors. Section 314.29 Covers and canopies mandates that all boxes and conduit bodies must be securely closed with covers or canopies to protect the conductors from physical damage and environmental factors. This section highlights the importance of maintaining the integrity of the entire conduit system, including the boxes and fittings. In addition to these sections, it is important to consider other relevant articles in the NEC when planning conduit runs for communications systems. Article 725, Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits provides specific requirements for low-voltage communications circuits, including the type of wiring methods permitted and the separation requirements from other electrical circuits. Article 800, Communications Circuits, covers the installation of communications circuits, including telephone, data, and other low-voltage systems. This article addresses issues such as grounding, bonding, and separation from power conductors to prevent interference and ensure safety. Article 820, Community Antenna Television and Radio Distribution Systems, provides requirements for the installation of coaxial cable and other components used in CAT-TV and radio distribution systems. This article addresses issues such as grounding, bonding, and surge protection to prevent damage from lightning and other electrical disturbances. Article 830, Network-Powered Broadband Communication Systems, covers the installation of network-powered broadband communication systems such as Ethernet over power line. This article addresses issues such as power limitations, wiring methods, and grounding to ensure safety and prevent interference. Now let's consider the practical implications of these NEC requirements for communications conduit bends. Firstly, when designing a communications system, it is important to carefully plan the conduit runs to minimize the number of bends. This can be achieved by using straight runs of conduit whenever possible and by strategically locating junction boxes and conduit bodies to break up long runs. Secondly, when bends are necessary, it is important to use the correct bending equipment and techniques to avoid damaging the conduit. Benders specifically designed for the type and size of conduit being used should be employed. The bending process should be performed slowly and carefully to prevent kinks or deformations in the conduit. Thirdly, when installing junction boxes and conduit bodies, it is important to follow the NEC requirements for sizing and installation. The boxes and conduit bodies must be large enough to accommodate the number and size of conductors entering them, and they must be installed in a manner that provides easy access for future maintenance and modifications. Fourthly, it is important to properly support the conduit runs to prevent sagging or movement. Conduit support should be installed at regular intervals, as specified by the NEC, and they should be securely fastened to the building structure. Sagging or movement of the conduit can put stress on the bends and connections, potentially leading to failures. Fifthly, it is important to use the correct fittings and connectors to ensure a secure and reliable connection between the conduit and the boxes, fittings, and equipment. Fittings and connectors should be listed for the type of conduit being used, and they should be installed according to the manufacturer's instructions. Improperly installed fittings and connectors can create loose connections, which can lead to electrical hazards. Sixthly, it is important to properly ground and bond the conduit system to prevent electrical shock hazards. Grounding and bonding should be performed in accordance with the NEC requirements, using approved grounding connectors and conductors. A properly grounded and bonded conduit system provides a low impedance path for fault currents, helping to trip circuit breakers and protect personnel from electrical shock. Seventhly, it is important to inspect the completed conduit installation to ensure that it meets all applicable NEC requirements. The inspection should include a visual examination of the conduit runs, boxes, fittings, and supports, as well as electrical testing to verify grounding and bonding. Any discrepancies or deficiencies should be corrected before the system is put into service. Eighthly, consider the type of communication cables being installed. Fiber optic cables, for instance, are more sensitive to bending radii than traditional copper cables. Consult the cable manufacturer's specifications for minimum bend radius requirements and ensure that the conduit installation complies with these specifications. Ninthly, coordinate with other trades during the design and installation phases to avoid conflicts and ensure a smooth workflow. This includes coordinating with HVAC, plumbing, and other electrical contractors to ensure that the conduit runs do not interfere with their systems. Tenthly, maintain accurate documentation of the conduit installation, including as-built drawings and records of all materials and equipment used. This documentation will be valuable for future maintenance and modifications. In summary, complying with the NEC requirements for communications conduit bends is essential for ensuring the safety, reliability, and long-term performance of communication systems. By carefully planning the conduit runs, using the correct bending equipment and techniques, and following the NEC requirements for boxes, fittings, supports, grounding, and bonding, the electrical and communication system can meet the code standards, prevent potential electrical hazards, and promote the longevity of the system. Let's talk about some specific scenarios to illustrate how these rules apply in practice. Scenario 1 involves a new office building being wired for both power and communications. The communications system includes a network of data cables and telephone lines. The electrical contractor plans the conduit runs for the communications system, taking into account the NEC requirements for conduit bends. Firstly, the contractor minimizes the number of bends by using straight runs of conduit whenever possible. Secondly, when bends are necessary, the contractor uses a conduit bender to create smooth, gradual bends that do not damage the conduit. Thirdly, a contractor installs junction boxes at strategic locations to break up long runs of conduit and make it easier to pull the cables. Fourthly, the contractor properly supports the conduit runs to prevent sagging and movement. Fifthly, the contractor uses the correct fittings and connectors to ensure a secure and reliable connection between the conduit and the boxes, fittings, and equipment. Sixthly, the contractor properly grounds and bonds the conduit system to prevent electrical shock hazards. 7thly, the contractor inspects the completed conduit installation to ensure that it meets all applicable NEC requirements. Scenario 2 involves the renovation of an existing retail space. The existing communications system is outdated and needs to be replaced. The electrical contractor removes the old wiring and installs new conduit runs for the updated communications system. Firstly, the contractor assesses the existing conduit runs to determine which ones can be reused and which ones need to be replaced. Secondly, the contractor carefully plans the new conduit runs to minimize the number of bends and to make it easier to pull the cables. Thirdly, the contractor uses a conduit bender to create smooth, gradual bends that do not damage the conduit. Fourthly, the contractor installs junction boxes at strategic locations to break up long runs of conduit and make it easier to pull the cables. Fifthly, the contractor properly supports the conduit runs to prevent sagging and movement. Sixthly, the contractor uses the correct fittings and connectors to ensure a secure and reliable connection between the conduit and the boxes, fittings, and equipment. Seventhly, the contractor properly grounds and bonds the conduit system to prevent electrical shock hazards. Eighthly, the contractor inspects the completed conduit installation to ensure that it meets all applicable NEC requirements. By following these steps, the electrical contractor ensures that the communications system meets all applicable NEC requirements and provides a safe and reliable communication network for the retail space. Now let's discuss the types of conduits commonly used for communication systems and their specific bending requirements. Electrical metallic tubing, or EMT, is a lightweight, unthreaded metal raceway commonly used for protecting electrical wiring. EMT is relatively easy to bend and install, making it a popular choice for many applications. The NEC specifies that EMT must be bent using a bender designed for that purpose to avoid damaging the conduit. The maximum number of bends allowed in an EMT run is the same as for rigid metal conduit, which is 4/4 bends or 360 degrees between pull points, such as boxes or conduit bodies. Intermediate metal conduit, or IMC, is a heavier gauge metal raceway than the EMT and provides greater protection for electrical wiring. IMC is often used in applications where greater physical protection is required, such as in industrial or commercial settings. Like EMT, IMC must be bent using a bender designed for that purpose. The maximum number of bends allowed in an IMC run is also 4/4 bends or 360 degrees between pull points. Rigid metal conduit, or RMC, is the heaviest gauge metal raceway and provides the highest level of protection for electrical wiring. RMC is typically used in applications where maximum physical protection is required, such as in hazardous locations or underground installations. RMC must be bent using a bender designed for the purpose, and the bending process requires more force than with EMT or IMC due to the heavier gauge of the conduit. The maximum number of bends allowed in an RMC run is 4/4 bends or 360 degrees between pull points. Flexible metal conduit, or FMC, is a flexible metal raceway that allows for bends and offsets in wiring systems. FMC is often used in short runs to connect equipment or to navigate around obstacles. While FMC is flexible, it still has bending limitations. The NEC specifies that FMC must be supported at intervals that prevent excessive sagging or movement, which can affect its bending radius. The number of bends in an FMC run should be minimized to avoid stressing the conduit and the conductors inside. Liquid-tight flexible metal conduit, or LFMC, is similar to FMC but has a liquid-tight jacket that provides protection against moisture and corrosion. LFMC is often used in wet or damp locations where protection from the elements is required. Like FMC, LFMC must be supported at intervals that prevent excessive sagging or movement, and the number of bends should be minimized to avoid stressing the conduit and the conductors inside. Non-metallic conduit, such as PVC conduit, is a lightweight, corrosion-resistant raceway commonly used for underground or direct burial applications. PVC conduit is easy to cut and join, making it a popular choice for many applications. PVC conduit can be bent using a heating process that softens the material, allowing it to be formed into the desired shape. The NEC specifies that PVC conduit must be supported at intervals that prevent sagging or movement, and the bending radius must comply with the manufacturer's specifications. The number of bends in a PVC conduit run should be minimized to avoid stressing the conduits and the conductors inside. In addition to these common types of conduits, there are also specialized conduits available for specific applications. For example, there is aluminum conduit, which is lightweight and corrosion resistant, and stainless steel conduit, which is highly resistant to corrosion and is often used in harsh environments. When working with any type of conduit, it is important to consult the NEC and the manufacturer's specifications for specific bending requirements and installation guidelines. Following these guidelines will ensure that the conduit system is installed safely and correctly and will provide reliable protection for the electrical wiring or communication cables.